Some milestones don't arrive with headlines. They happen quietly, far from our daily routines, and only later do we notice what they imply. This one belongs to Voyager 1. Voyager 1 is a machine from another era, built with the assumption that anything can fail, and the design has to survive anyway. It launched in 1977, and it kept going. Not because it's magical, but because it's simple enough to endure, and careful enough to prove something that other spacecraft only suggest. It has become a moving reference point, a ruler we can hold up against the universe and ask, how far have we really gone? That question matters because our feelings about space are often shaped by stories. Stories compress distance. Stories skip the boring parts. Stories make interstellar travel seem like a problem of willpower or funding. Reality does not montage. Right now, Voyager 1 is traveling at a pace that sounds huge until you place it against interstellar space. It's moving at 37,904 miles per hour. That is fast enough to make Earth feel small. But Earth is not the problem. The gap between stars is the problem. After 48 years, Voyager 1 has reached a distance where a radio signal needs about 1 day to reach it. That distance is a light day, the distance light travels in 24 hours. Notice what that means operationally. Every command is delayed, every confirmation arrives late, and even small troubleshooting becomes a slow exchange of messages. There's no real-time joystick. There's patience, planning, and waiting. So here's the question that lands like a stone in the stomach. If 48 years buys us 1 light day, what does it cost to buy 1 light year? Stay with me. The math is simple, but the conclusion reshapes how you hear every promise about reaching the stars. We use light year casually, as if it's just another long distance. But it's a distance unit that carries a warning label. A light year is not the time it takes to travel. It's how far light travels in a year. Light is the fastest thing we know. So when light needs a year, what chance does a spacecraft have? 1 light year is about 5.84 trillion miles. Those words can roll off the tongue and still leave you with no intuition. Trillion is beyond what our everyday brain is built to handle. So instead of trying to feel the number, ask a different question. What does it do to the idea of progress? On Earth, speed changes everything. Faster ships turned months into weeks. Faster planes turned weeks into hours. That curve trained us to expect that the next improvement will always shrink the map again. But space is where the curve flattens. You can go faster, and it still feels like standing still. Voyager 1 is the most convincing proof we have, because it is not hypothetical. It is already out there, already traveling, already paying the price of distance in real time. Hey, if you're fascinated by the science and stories behind space exploration, subscribe and enable notifications so you can join me on every new discovery. A cleaner way to think about this is to compare distances inside one consistent mental model. In that model, Voyager 1 isn't gone. It's farther down the same street, still inside the territory dominated by our sun. Now compare that to the nearest star, not a galaxy, not a distant target, just the closest neighbor. On that scale, the nearest star sits around 4.2 light years away, about 25 trillion miles. Between here and there is no comforting sense of terrain. It's not a journey through places, it's a crossing through emptiness. And emptiness is not safe. At high speed, even tiny particles become hazards. Radiation becomes a slow pressure on materials and electronics. So the gap is both wide and hostile. Wide enough to break our schedules, hostile enough to punish our mistakes. That's why interstellar travel is not one engineering challenge. It's many challenges stacked on top of each other. Now here's the retention hook, because this is the point where your intuition either adjusts or it tries to escape. Voyager 1 reached a light day in about 48 years. A year has 365 days. So to estimate 1 light year at Voyager 1's pace, you multiply, that's it. Multiply 48 by 365. The result is about 17,500 years for 1 light year. That's not a travel time, it's a cultural era. It's longer than most of what we call history, and 1 light year is not the target anyone truly wants. The nearest star system is about 4.2 light years away. So at Voyager 1's pace, you're looking at roughly 74,000 years for the nearest neighbor. And here's the part most people don't say out loud. A mission that lasts that long isn't a mission anymore. It's a rumor drifting through time. No machine we've ever built is designed to operate for 74,000 years. Power systems degrade. Storage becomes unreliable. Tiny failures multiply. Materials fatigue. Radiation quietly changes electronics over long exposure. So even if a probe crosses the distance, it won't arrive as an active explorer. It arrives as a silent artifact. Distance turns exploration into archaeology. This is also why the phrase, "we just need better rockets," can be misleading. Better rockets help inside our solar system, where travel times still fit inside careers, budgets, and political cycles. Between stars, time is the enemy as much as distance. You don't just need speed, you need reliability across eras. You need systems that can be repaired without spare parts. You need navigation that stays accurate for generations. You need software that doesn't become obsolete before arrival. And you need all of it to work while the craft is constantly exposed to a background of radiation that never stops. So the crossing is not one challenge, it is a chain of challenges where the weakest link determines the ending. This is where people propose the generation ship. If one lifetime can't do it, you send a society. A traveling habitat sounds heroic. It sounds like determination. It sounds like refusing to accept limits. But determination isn't the same thing as stability. Try to keep 5,000 people healthy and cooperative inside one closed system for 74,000 years. That requires more than engineering. It requires culture to remain coherent, leadership to remain functional, and conflict to remain survivable forever. On Earth, civilizations can transform beyond recognition within 500 years, even with open skies, trade, and endless land. Languages can drift dramatically over 1,000 years. Meanings change, priorities reorder, traditions mutate. So, at 10,000 years, the original mission is already a legend. At 20,000 years, it's an origin story, something people inherit, not something they chose. By 50,000 years, the ship has its own identity, and the destination is just a concept at the edge of belief. Even if the ship never fails mechanically, the culture inside it can still fail to care, and a mission without belief becomes drift. A generation ship isn't just a vehicle, it's a civilization sealed in a bottle, asked to remain sane, focused, and functional for longer than civilizations normally last. So we reach for the escape clause, go faster. Let's assume the future delivers propulsion that feels unbelievable by today's standards. Let's say we reach 10% of the speed of light. That's about 67,108,089 miles per hour. At that speed, the universe stops looking empty. It starts looking dangerous. Dust becomes a threat. Rare particles become hazards. Shielding becomes a life or death requirement, not a design preference. But even with that speed, distance still collects its fee. At 10% light speed, 1 light year takes 10 years. So 4.2 light years becomes 42 years, one way. Then the practical parts arrive. You must slow down, or you fly past your target. You need time at the destination. You need redundancy. You need the crew to survive deceleration after decades of travel. That is how you reach the range of 90 to 100 years. Even with near-miracle propulsion, the nearest neighbor is still a lifetime scale commitment. Now widen the target to something 40 light years away. At 10% light speed, that's 400 years, which forces you back into multi-generation planning again, even after you solved propulsion. So propulsion is not the only wall. Time is a wall, longevity is a wall, human continuity is a wall. And there's a subtle trap here. When people hear about faster propulsion, they focus on the headline number and assume everything else stays familiar. But as speed climbs, the environment changes. The risks change. engineering requirements change. So you don't simply scale up a familiar spacecraft. You build a fundamentally different kind of machine, one that can survive a new kind of travel. That's why Starflight is often described as the hardest project imaginable. It's not a bigger plane, it's a new category of survival. Now for the twist that makes the situation feel even more extreme. People say Voyager 1 left the solar system. In one sense, it has. It crossed the heliopause and entered interstellar space. That boundary marks where the sun's solar wind finally gives way to the interstellar medium. But the solar system is more than the planets. It is the full gravitational reach of the sun. The Oort cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units, and its outer boundary may lie between 10,000 and 100,000 AU. Those ranges matter because they imply something counterintuitive. The sun's domain stretches outward toward nearly a light year. At Voyager 1's current pace, it won't reach the inner edge for about 300 years, and it won't clear the outer edge for maybe 30,000 years. So in a meaningful sense, our most distant probe is still moving through the sun's outskirts. We're proud of how far we've gone, and we should be, but the map barely notices. This is where the "where is everybody?" question stops sounding like a mystery and starts sounding like logistics. If typical separations between civilizations are 1,000 or 2,000 light years, communication itself becomes slow and fragile. Even light turns conversation into a message that outlives its sender. Signals arrive late, context is missing, responses are always outdated. It's less like a dialogue and more like exchanging artifacts across eras. Space doesn't connect. Space isolates. A galaxy full of life could still feel empty, simply because distance erases familiarity before it can become normal. This is also why we should be careful with the word frontier. On Earth, a frontier suggests a line you can cross and then settle behind. It suggests expansion that happens step by step with supply routes and backup plans. Between stars, a frontier doesn't behave like a line, it behaves like a gulf. If you send a probe, it becomes a one-way bet, a long, quiet coast through darkness where the craft must survive without help. If you send humans, the problem is not courage. The problem is continuity. A crew has to stay alive, healthy, and psychologically stable, while the outside world becomes more distant with every hour. Even the concept of home changes under that kind of separation. Home becomes a memory, then a myth, then a word whose emotional weight shifts over time. And if the mission succeeds, success itself is strange. You arrive somewhere new, but the culture that launched you is gone. The world that funded you has moved on. Connection is cut by time, not just by distance. So interstellar travel isn't only about reaching a destination. It's about accepting that the destination may never be shared with the people who began the journey. That reality pushes many thinkers toward a quieter ambition: exploration without travel. We can learn enormous amounts by observing, by building better telescopes, better sensors, better ways to decode faint signals. We can map atmospheres, estimate temperatures, and infer the chemistry of worlds we will never touch. That sounds less romantic than a starship, but it might be the most honest version of how a species learns what's out there. Voyager 1 even hints at a different kind of legacy, the legacy of presence rather than arrival. A small craft can carry a message, a record, a clue that we existed, not because we expect an answer quickly, but because leaving evidence is sometimes its own form of connection. So the big question is not only how do we get there, the deeper question is, what kind of civilization do we want to be, given the limits? Do we build myths about escaping, or do we build systems that protect the only world we can reach on a meaningful timescale? Because once you accept the travel math, the priorities shift. The stars remain real, they remain reachable in theory, but in practice, the cost is so high that it changes what responsibility means here on Earth. Voyager 1 will keep drifting long after its instruments go quiet. In 40,000 years, it will pass relatively close to another star, close only by cosmic standards. By then, Earth may be unrecognizable to us, history doesn't pause, and biology doesn't wait for a spacecraft. Voyager 1 becomes a symbol of two truths at once. First, we can build something that endures. Second, the universe is not built for quick escapes. That is why the most dangerous lie is the casual idea that we can ruin Earth and simply move. There is no easy interstellar plan B, not on the timescales that matter to a human life or to a human civilization. If we want a future, it starts here, because the distances don't forgive shortcuts and they don't care about optimism. Speaking of Voyager's incredible journey, there's something unsettling happening to our most distant spacecraft right now. Its systems are failing one by one, and what it's detecting at the edge of interstellar space raises more questions than answers. Watch our video on the scary truth about the Voyager 1 probe to discover what awaits in the void between stars.